Welcome to today's lecture. In previous lecture, we discussed about the definition for heat transfer, the driving force for heat transfer, the modes of heat transfer, and today's lecture we are going to discuss about Fourier's law of heat conduction, then the rate of heat flow through a plane wall and composite wall. First I will start with Fourier's law of heat conduction. This law states that the rate of heat flow Q is directly proportional to the area of heat transfer A, temperature difference dT, and inversely proportional to the rate of that is the direction of heat flow or the path of heat flow, that is dx. In this equation, Q is equal to minus Ka dP by dx. Here this proportionality constant K is nothing but thermal conductivity of the material, and the unit SI unit is watt per meter cube or degree Celsius, where A is the area in meter square, dt is the temperature difference, dx is the thickness of the material, which is in meter. Q is the rate of heat flow or rate of heat transfer, that is in watts. If you want to find any that is heat transfer rate in any of the geometries like plane wall, composite wall, cylinder, composite cylinder, sphere, and so on, you should use this. The basic equation to find rate of heat flow is Fourier's law. With the help of this law, we can be able to find the rate of heat flow in other materials or dimensions. Before going to the derivation of rate of heat flow to a plane wall, just I want to tell you about two important things. One is steady state, another one is unsteady state. Steady state heat transfer means the temperature does not change with respect to change in time. Temperature does not change. Temperature remains constant. Whereas when time changes, temperature remains constant. In unsteady state, temperature changes with respect to change in time. Most of the heat transfer are taking place by unsteady state initially, and after that it reaches steady state. So most of the heat exchanger designs, when designing heat exchangers, they will follow this steady state heat conduction. In coming lecture, while discussing about derivation of that is rate of heat flow through a plane wall, composite wall, cylinder, composite cylinder, we will consider steady state heat conduction. First we will start with plane wall. Let us consider the plane wall. The thickness of the wall is gauge, which is in meter. We assume that Z is the hot face, hot side or cold side, or hot face. This one is cold face or cold side. Let us assume the temperature is T1 at the hot side and T2 at the cold side. once this plane wall, the heat transfer takes place and plane wall reaches a steady state, you can get a curve like this. Then let Q be the rate of heat flow through the plane wall. To find out the expression for rate of heat flow through plane wall Q, we should know the Fourier law of heat conduction. Q is equal to minus Ka dT by dx. Let this equation be 1. Just to rearrange this equation 1, Q dx equal to minus Ka dT. Here x is equal to 0 and x is equal to dx. If you integrate this equation 2 between the limits 0 to x and t1 to t2, 0 to x you will get 2x equal to minus Ka into minus T. And this equation can be written as Q is equal to Ka T1 minus T2 divided by x. This is the rate of heat flow through a plane wall. We can rearrange this equation in other form also. That is Q is equal to T1 minus T2 divided by x by K. Whereas in this equation, the numerator is T1 and T2 are the temperature difference. This initial, there is hot state temperature T1 and T2 is cold state temperature. That difference is T. And this denominator term x by Ka referred as thermal resistance. RTH, thermal resistance. So, the equation for the rate of heat flow to a plane wall is Q is equal to T1 minus T2 divided by x by K. In this equation, x is the thickness of the material, K is thermal conductivity of the material of the plane wall, A is the area, and T1 is the temperature of the hot side or hot phase, and T2 is the temperature of the cold side. Okay. This is also written in other form, delta T by RTH in thermal resistance. Okay. Next one, heat flux. Heat flux is denoted by letter small q. There is rate of heat flow per unit area. The unit for heat flux is watt per meter square. While solving some problems, you will use this heat flux equations. Okay. The next derivation is finding Q in composite. Previously discussed about the rate of heat conduction through plane wall. Here is composite wall. Composite composite wall is nothing but over a wall, single wall, if you place more layers, then it becomes composite. In chemical industries, most of the heat exchangers or furnaces are made of composite materials and composite walls because to avoid the heat loss. This is the first layer. Just to assume there are two layers are placing over the wall. This is the wall. The second layer and this third layer is made of different materials. insulating materials to avoid the heat loss, and you assume that inside of this wall is the hot side and the outside of the wall is cold side. Let Q be the rate of heat flow. Let X1 be the thickness of the first layer, X2 the thickness of the second layer, and X3 be the thickness of the third layer. Let T1 is the temperature of the hot side, T2, T3 and T4. The outside temperature of the cold side is T4 and inside is T1. This T2 and T3 are interface temperature, the temperature between the layer 1 and 2 and 2 and 3 respectively. T1 is greater than T2, greater than T3, then T4. Let Q1 be the rate of heat flow in layer 1, Q2 and Q3. Here, since we are assuming some steady state heat conduction, let Q is equal to Q1 is equal to Q2 is equal to Q3. The rate of heat flow in each layer are same, and let K1 be the thermal conductivity of material 1 on layer 1, K2 for layer 2 and K3 for layer 3. With this, we can able to find the expression for rate of heat conduction through the composite wire. For this, again we have to consider Fourier's law of heat conduction equation. It is denoted by Fourier's law of heat conduction equation. Q is equal to minus Ka dt by dx. Deriving, considering all the three layers, it's very difficult to attain the final expression. If you separate this layer, layer 1, layer 2 and layer 3, and again adding all the three layers, then it's easy to find out the expression. Just for first I start with layer 1. Layer 1, Q1 is the rate of heat. Q1 is equal to minus K1. Thermal conductivity of the material. 1 suffix 1 indicates the layer 1. Let A be the area of the heat transfer area and dt by dx. So rearranging Q1 dx equal to minus K1 A dt. You integrating it is the limit 0 to x, so 0 to x1 and T1 to T2. Value is Q1 is equal to T1 minus T2 divided by x1 by Q1. This is rate of heat flow at layer 1. Similarly, you can write the expression for layer 2. Just try to do this. Layer 1, Q1 is equal to T1 minus T2 divided by x1 by K1. For layer 2, by integration, and you will get Q2 is equal to T2 minus T3 divided by x2 by K3. For layer 3, Q3 is equal to T3 minus T4 x3 by K3. These are three equations we will get for on the layers If you add all these three layers, Q1 plus Q2 plus Q3 equal to the right hand side, and equating this, rearranging T1 minus T2 plus T2 minus T3 plus T3 minus T4 divided by x1 by k1a plus x2 by k2a plus x3 by k3a. You just cancel. You will get T1 minus T4. Finally, there is Q1 is nothing but Q, and Q2 also. Q1 Q equal to Q2 is equal to Q3, and you can write the heat flow as, because it's steady state, the rate of heat flow in each layer is same. So you can write, instead of Q1, Q2, Q3, you can write Q, T1 minus T4 divided by x1 minus k1a, x2 by k2a plus x3 by k3a. You can see here the denominator term, when the layer increases, the resistance also increases. If it is a single layer or a plain wall, in previous derivation we have seen only one term, that is thermal resistance term, the denominator is x by K. Here we have three layers, so three resistance terms are here. Suppose if you add another layer, that is fourth layer, then it becomes 4 resistance at the denominator and becomes x4 by k4a. Okay. In simple form, you can write Q is equal to the delta T temperature difference by thermal resistance. Okay, next lecture we will see the derivation of heat conduction through hollow cylinder. Thank you.